Welcome ENAT 140 Operational Amplifiers at Bellingham Technical College. In this lecture I'll be going over a few examples of decibel gain, both power and voltage, using the examples from our textbook, James Fiore's Operational Amplifiers textbook. And I'll be using a nice program known as SMath. This is a free program that is a type of what's called MathCAD software. So it looks like just a piece of paper, but what it really has are embedded functions, just like Excel spreadsheet, that enables you to define variables and write in equations that can be solved for whatever your input is. So I'll be walking you through a little bit of how that works. So some of what I have here is just text, such as these boxes, but others are defined variables. You can tell by the colon in front, and equations that invoke those variables and do your calculations for you. I'll add another note. You'll see some blue units associated with several different variables, those that should have units. And a nice thing about SMath is it has units functions and will do your units analysis for you and help you error check. So it's another reminder to always include your units and use them when you solve a problem. So we'll go ahead and start with the first question. This is example 1.1 in our textbook. So we're told that an amplifier has a power gain of 800. So that's ordinary gain. So that's P out over P in. How would we express this in decibel gain? Well, this is a real simple application of our 10 times log base 10 of our ordinary gain example. So we've defined our ordinary gain G as 800 and written our expression for decibel gain in terms of ordinary gain, and SMath calculates our result as 29. So 29 decibels is equivalent to 800 as a ratio gain. And just to give you an example of why SMath is a nice way to do this, if someone were to say, well, gosh, my amplifier isn't maybe working quite so well, what would be the decibel gain if maybe my ordinary gain was only 500? So all I have to do is change my input, and you can see here the power of using the decibel scale. Maybe I'll go ahead and cut my ordinary gain down to 400. So rather than a power out over power in of 800, now it's only 400. Maybe we lost some power in our amplifier, something overheated, and we have more resistive losses. So our decibel gain dropped from 29 to 26. Ooh, remember that halving. So if you cut something in half, you will lose 3 decibels. So there's another example of that. So we'll gain it back. Okay, I've added the what's called head calculation method that Mr. Fiore uses. If you are used to expressing things in terms of exponents, you could take that 800 and you could express it as 2 cubed times 10. And then break up the calculation and then use your kind of handy reference of doubling equals 3 dB and a gain of 10 equals 10 dB, and then come up with the 29 using the rules of exponents. So if you didn't have your calculator with you, you could convert that 800 to 29 just using your rules of exponents and a couple of handy conversions, that doubling and halving the plus 3 dB and minus 3 dB. Generally speaking, I've used the calculator for everything, but again, knowing these rules of thumb is important, and we'll definitely be utilizing the plus and minus 3 dB when we reference our half power upper and lower critical frequencies when we're looking at how gain of an op-amp changes with our input signal frequency. So stay tuned, we'll be using that 3 dB again. Okay, next example. We're given an attenuator, which is basically an amplifier working backwards. It reduces signal, and we're told that it reduces signal power by a factor of 10,000. How do we express this as a dB loss? So we can express, we can use some exponents. We can say, okay, our gain, our ratio gain is going to be 1 over 10,000 because it's a loss. So our P out is 1, P in is 10,000. So this is 10 to the minus 4. So we throw this in for G, 10 to the minus 4 for G, and take the log base 10 of that, multiply by 10, and we get negative 40. So we could look at that argument there and say, based on what we know of the definition of log base 10, what we're really saying is, what power would we have to raise 10 to get 10 to the minus 4? Well, minus 4. So you really didn't need to use your calculator there. So the log base 10 of 10 to the minus 4 is minus 4, and then we multiply 10 by that and we get minus 40. And so it's good that we're seeing a minus sign because this is an attenuator. So we're getting a gain of minus 40, which is the same thing as an attenuation of power. We're decreasing it. So now we get to go the other way. We're told we have an amplifier with a 23 decibel gain, and now we need to know the power output for a given input, which means we need to know the ordinary gain, the ratio gain, to apply that and get an actual single wattage level for power out. So again, pretty easy. First we define our variables. So this time we're going to define our decibel gain ahead of time. There's 23, and we've defined a power in as 1 milliwatt. So 1 times 10 to the minus 3 watts is 1 milliwatt. So if we invert our gain equation and basically solve for ordinary gain G in terms of decibel gain, our properties of log base 10 says we could get our ordinary gain by basically raising 10 to the power of whatever our decibel gain was divided by 10. So this expression here is basically our inverse of the decibel expression. And again, we get this just by simply using our mathematical definition of logs and antilogs. So now that we have an expression, we can just plug our variables in, and if you look at this, it's actually got the colon, so this is actually a mathematical function. SMath is taking our value for dB here of 23, and it's applying this equation. It's giving us an ordinary gain of 200. So wow, that's pretty high gain. It's kind of what we would expect maybe from a BJT beta. So maybe this was maybe this power. We don't know whether we're getting more current or voltage being amplified. This could be maybe a common emitter or a common base small scale amplifier. We don't know what it is, but those would fit the bill. So if we want P out, we just multiply ordinary gain by P in. And so we have 200 times 10 to the minus 3, or 2 times 10 to the second times 2 to the times 10 to the minus 3. So that's like 2 times 10 to the minus 1, or 0.2 watts. So gains are dimensionless. Power in and power out are in watts. So we have the right units. Okay, example 1.4, we have a 3-stage amplifier. So this is a cascaded amplifier. And each stage has a different gain. So we have 10 dB, 16 dB, and 14 dB. And we want to know what the overall gain is. So we got two choices. We can either convert those decibel gains into ordinary gains and multiply them, or we can remember what our rules of logarithms are and know that they would just be additive. And we can kind of maybe try doing it both ways and hopefully get the same number. So I started by just defining my variables. So I defined a dB1, dB2, and dB3, with the given decibel gain ratios. And I went ahead and converted to ordinary gain. So my dB1 of 10 gave me a gain ratio of 10. My 16 decibels gave me a gain of just under 40, ordinary gain, and then 14 gave me dB gave me about 25 in just ordinary gain. So I know that if I'm looking at gain ratios for a cascaded amplifier, I would multiply those. So if I multiply them all and I only keep one significant figure, I've got about 10 to the fourth. So if I apply the decibel scale to that, I'm going to end up with log base 10 of 10 to the fourth, which is 4, and then I multiply 10 by that and I get 40. So let's see if that's the same as adding up 16 and 14 and 10, and yes it is, because 16 and 14 is 30 and add 10 to that is 40. So I can add the decibel gains or I can multiply the ordinary gains. So we kind of just proved that relationship. Okay, example 1.5, we're given an amplifier that has a signal input of 50 millivolts and an output of 2 volts. And we want to know what the decibel voltage gain is. So remember, we got a voltage ratio, but when we express in decibel gain, we're going to be expressing in equivalent power. So here's where we haul out our 20 multiplier. So beyond that, it's pretty easy though. We got our V out and our V in, so we make a ratio, and here's our ordinary voltage ratio, our A sub V, that hopefully we're all used to from small scale amplifiers and semiconductors. So we plop that in. We got our 20 multiplier that gives us equivalent power, and so this is AV prime. I had to write out the prime. It's 32. So 32 decibels is the same as 40 ordinary. And you can go right through these. These are all spelled out in Mr. Fiore's book. I've just walked through them here because I might do them a little bit different and just kind of wanted to explain to you all, but this shouldn't be anything different than is in your textbook. But these are some interesting problems that are very relevant for what you would be seeing in the workplace, wrangling gains. So example 1.6, we got an amplifier with a 16 dB gain, and somebody gives us a 10 millivolt input signal, which is pretty typical for some small signal maybe coming from an instrument that needs amplifying. So what's our output voltage? Maybe we got to make sure it doesn't clip or something like that. We need V out. Okay, so we're looking at voltage ratios and we have a decibel gain. So that decibel gain is a power equivalent. So we got to haul out our 20 times log of the voltage ratio. And we apply that and we get a 200 millivolt output. So 10 millivolts to 200 is 20. So we should have an ordinary voltage ratio gain of 20. So 0.2 volts output. A power amplifier has a power output of 120 watts. That's a lot. That's like an old incandescent light bulb. How would we express this power in dBW? Ooh, okay. It's not a gain this time. Now we're doing that power versus a reference. So it's just power. There's no gain. It is an amplifier, so obviously it's giving us a gain, but we're just expressing that wattage on a decibel scale. And somebody said, I want to use a 1 watt reference. That's what the dB capital W means. So say okay. I can do that. My P out is 120 watts and my reference is 1 watt. So my dBW is just my ordinary, not ordinary, I should say, my decibel expression, which is 10 times log base 10 of my ordinary ratio. So my power out is 120 divided by 1 watt. 120 watts divided by 1 watt is 120. So log base 10 of 120 times 10 is 20.8. So I can say dBW 20.8, or I can say 120 watts, and I've said the same thing, or equivalent thing. So someone has a small personal music player that delivers 200 milliwatts to its headphones. So what is the power output in dBW and dBm? So the first thing we know is we've got two different references. So we're just expressing power, so we're not thinking about gain, but we have a different reference number. So we're going to express this 200 milliwatts or 0.2 watts, and then we're going to ratio it to 1 watt in one expression and to 10 to the minus 3 watts in the other. So here's where we have it. This is our dBW. P out is 200 times 10 to the minus 3 watts. That doesn't change. It's in both expressions. And that's how it's defined up here. And Our dBW is going to use a 1 watt reference. So we're going to be taking the log base 10 of, a fairly small number, but not too small. And then in this one, we're going to be dividing by 10 to the minus 3, because 10 to the minus 3 watts is 1 milliwatt. So that's going to be a much bigger ratio. Effectively, we're going to be multiplying P out by 1,000 and taking a log base 10. So we get 23. So that also is telling us something about what we're multiplying by when we have that difference in the denominator. So we can use our properties of natural logs to create a generic expression for the difference between dBm and dBW if we wanted to, or we can just plug in the references. Now, just as an aside, dBW and dBm are fairly standard. It means reference to 1 watt or reference to 1 milliwatt. You could use any reference you wanted. You could say, hey, express that power on a decibel scale reference to 1/4 of a watt or 1/2 a watt or 1,000 watts. Doesn't matter. You just put whatever that reference is in the denominator. So this time it was these two. Okay, example 1.9. A studio microphone produces 20 dBm signal while recording normal speech. What's its output power? Maybe we're wanting to make sure we're not putting out too much power and deafening somebody. It is a studio talking about human speech. So 12 dBm. So that's going to be 12 is going to be equal to 10 times log base 10 of the output power divided by 1 milliwatt. I can rearrange what I just said and solve for power out over power in by raising that dBm number over 10, putting it in the exponent, raising 10 to that. So I'm basically using, let me scroll back up, I'm using this expression, except G now is P out over P in, and I'm given a P in. So the P in comes over and multiplies. So here's my 1 milliwatt that was my reference for my dBm. Here's the number I'm given, divided by 10 for the 10 out front in my original expression. I'm raising 10 to this ratio, and I end up getting about 0.016 watts. So that would be the output. So we're rolling in that gain. So basically this is just an example of how to use the inverse of the dB power scale with the milliwatt reference in there. So this problem is just another way of applying our anti-log expression for decibel gain. So it's like example 1.3, except instead of a gain, a power reference. Okay, last but not least is a test oscillator. So this is something basically what we don't want amplifiers to do. That's why we use negative feedback, so we don't get oscillation. So if we give an amplifier positive feedback, it'll oscillate and produce a periodic waveform, which might be useful if we need a signal for a function generator. That's one of the things your function generator is doing for you. But it's giving you a 2-volt signal. So for those of you who are using the Picotex Picoscope for any of your labs, you will be very happy that you can get a 2-volt signal from your oscillator in your arbitrary waveform generator. So how would we express that signal value as a dBV value? So when we see dBV, we know this is a voltage reference to 1 volt. But because it's dB anything, it's equivalent power. So if I'm going to use a voltage versus a power ratio in the argument of the log, I have to use the 20. So the voltage of the oscillator is 2 volts. Our reference signal, our reference voltage is 1 volt, because that was indicated by the capital V in the dBV. And I have the 20 multiplier log base 10 because I'm on the decibel equivalent power scale. And so I just solve this equation and I get 6. So our 2 volts is also dBV of 6. Oh, had a couple more. Okay, example 111. A computer hard drive read-write amplifier exhibits a gain of 35 decibels. We've got an input signal of negative 42 dBV. So this is pretty small, even though we have the 1 volt reference. What's the output? So we kind of need that A sub V voltage gain. So we can either go back and forth with adding and subtracting the decibel scale, or we can convert everything to ordinary gains, remembering where to use our 10s and where to use our 20 multipliers, and then multiply out and reconvert. So I started by defining my variables. What I was given, I was told I have a dBV input of negative 42, and I have an AV prime, which is the decibel scale voltage gain, 35. So now I'm going to redefine my input as an ordinary voltage. So I'm going to back out that 1 volt reference in the dBV scale. So I'm just going to go from dBV to just volts. So I get about 8 millivolts. So negative 42 is about 8 millivolts. Then I'm going to convert. I decided to go with ordinary expression. So then I converted my AV prime to just an AV. And the 20 under here is the result of the fact that I'm using the 20 multiplier, right? Because I've got a voltage gain, but decibel scale is power, so I've got to have the 20 under there. So this is the anti-log, the way to go to get ordinary from decibel. So here's my decibel voltage gain. I got to divide the 20. I raise 10 to that power, which effectively accomplishes the anti-log mathematical function, and that gives me the ordinary voltage gain of 56. So voltage gain is V out over V in. I have V in, I have voltage gain, so I can get V out by just multiplying those two together. So here's my output voltage as a voltage, and I can express it as a dBV by going back into my definition for dBV. Here's my 1 volt reference, and that's a negative 7. So, well, that's a lot of work. Had I been more confident, I could have just said, well, I know that I can add decibel scale gains, and so I could have just simply used my dBV input plus the decibel gain and gotten negative 7. So negative 42 plus 35 is negative 7. So I got the same number both ways. So you can see how much easier this one was. So here's an advantage of using decibel expressions. And that's probably why somebody expressed their input signal as negative 42 dBV instead of as 8 millivolts, because they could get their output voltage in dBV by just adding the voltage decibel gain rather than going through all of these conversions. Okay, good application of properties of logarithms. So here's an electronic instrument. We have a guitar power amplifier, and it needs an input of 20 dBm, so milliwatt reference. So here's a power to achieve an output of 25 dBW. Okay, so that's a different reference. What gain do we need? So we can't just add and subtract these because we've got a different reference. But what we could do is we could kind of derive for ourselves what's the relationship between dBm and dBW, because if we had that, then we could just add the overall power gain. So let's see if we can't just kind of work that out. Let's scroll down to that, and I work that with an example of 5 watts. So I can write an expression for dBm or decibel power reference to 1 milliwatt. So I'm going to say, okay, you got whatever power you got, and here's your 1 milliwatt reference. Well, 1 milliwatt is the same as 10 to the minus 3 watts. Okay. oh hey, I've got a quotient. Hey, I know that I can use the properties of natural logs to take this quotient and turn it into just log base 10 of power minus log base 10 of this 10 to the minus 3. So let's do this over here. And I keep the same 10 multiplier. I won't factor that out. So I've got this expression where I used my quotient to break it up. And this should really be a negative sign here. And then I can take my minus 30, or my minus 3, excuse me, and use another property of natural logs and have that come down as a multiplier. So now we have minus 30 log base 10 of 10, and that ends up giving us effectively, with a power expression of 5, we end up with 23, but more importantly, log base 10 of 10 is 1, and we now have a 3 multiplier coming down times 10, so it's 30. So if we subtract 30, we can go from a dBW to, a dBm to a dBW, so our conversion factor is 30 in this case. So there may be a sign error in here, and I apologize. It will be corrected in the file input in Canvas. So example 1.12 goes into that and uses that relationship. Generally speaking, if you're not quite sure how to add and subtract something in decibel scale, you can always convert back to ordinary expressions or gain ratios and do your multiplying that way. And so that's what I defaulted to. So I took my power input in dBm and got a 0.1 watt and gave myself an expression for the power output, same thing, got an ordinary gain ratio, and then just converted to decibel scale and got 35. So that's kind of the sure thing way of doing it. So I will leave it up to you all to look and see how you would use that 30 factor in relating the dBm to the dBW to maybe work this problem without having to convert from dB to ordinary. And that is it for examples. Again, these are all in Mr. Fiore's book. This file will be available both in SMath and in PDF on Canvas, so you can look this over and work it yourself. If you have SMath, feel free to change inputs and see how things change. And would highly encourage you to learn how to use these types of spreadsheets, because they're a great way of writing out your equations and getting to know how to step through calculations without necessarily having to do a lot of handwriting if you end up having hand physical problems. But that is just a recommendation. So that is it for decibel gain. Power, voltage, we didn't go through any current examples, but that would work like voltage. So next topic will be our next section in James Fiore's chapter 1 of op amps, and we're going to look at frequency response of gain. So we've defined gain on the decibel scale. Now we're going to look at decibel gain as a result of an amplifier acting on signals of different frequencies, and we'll see that decibel gain changes depending on the frequency input, the signal that we're trying to amplify. So we'll look at that next time.